So I think now we can continue in the original sequence. That means paper C13, paper C14, and finally paper B3. That means just the next paper will be given from Hoffer, Lobos, and Gutsi, and the title is Chemistry of Intermediates on Formation and exchange of methanol over platinum, niobium oxide, aluminium oxide. Please, Mr. Hoffer, you may start.
Chairman, ladies and gentlemen, some members of our research group are quite interested in alcohols. I mean not only the wines, but the formation and further reactions of methanol. We believe that if we need some information on the alcohol formation, we should study some other reactions of the alcohols as well. For example, the catalytic exchange of the hydrogen atoms in the alcohol, in the methanol, to deuterium. From some previous studies, we concluded that there is a bridge-type chemisorption of methanol on the metal support interface on platinum aluminum oxide catalyst. If we consider the different materials in this catalyst, so deuterium exchange proceeds on aluminum oxide alone, but it is always a single exchange. Only the OH, the hydrogen in the OH group is exchanged because methanol can be sourced on the Lewis acid cycle of alumina. And the exchange proceeds also on the platinum alone, for example on platinum black, but it is also not a very fast reaction, and also the vast majority is the monodeuteriated product. When we put these two materials together on the platinum aluminum oxide, we have a much higher rate of exchange, and the rate of the multiple exchange is much increased, so that is the formation of the methanols containing 2, 3, or 4, even 4 deuteriums instead of only one. We concluded that an important mechanism of the exchange which improves the selectivity of the multiple exchanges, that the bridge type chemisorption of the methanol. Platinum supports the activated deuterium for this process. Now, we would like to study further the reactivity of the different bonds in the methanol molecule, the CH-OH group bonds, and we try to modify the above catalyst. So we would like to find the correlation between methanol dispersion, niobium content, preparation methods, treatment, and reactivity. We, as a modifier for the platinum aluminum oxide catalyst, we choose the niobium for some reasons, because this oxide can be partly reduced and can migrate to the metal surface, so we can expect that that we can modify the metal support interface with niobium oxide. We applied several methods to characterize the catalyst, and we carried out different reactions, CO hydrogenation, deuterium exchange of methanol, and just for the comparison, deuterium exchange of methane. We changed the platinum content of this catalyst samples and the niobium content, and we used catalyst samples with and without chloride. These are the catalyst compositions. They are not really important to study, just it's just an illustration of the catalyst study. We applied different treatments of the catalyst samples. The samples were in situ oxidized and reduced at 2 different temperatures, so there are 4 combinations. Shortly, first the temperature of the calcination and then the temperature of the reduction. can be seen. First, let me show you some data on the catalyst structure, because if you want to know something about the reaction itself, first we have to study the catalyst structure. So, from PPR measurement, we can see that addition of niobia helps the reduction of the platinum. So, with increasing niobia content, the temperature of the maximum reaction rate is decreasing for all the samples. And I don't mention now the effect of calcination temperature. It is not really surprising that easier reduction results in bigger particle size. So we determine the dispersion by CO chemisorption and plot it against the niobia content. We can see that generally higher niobia content means lower dispersion. An exception is the 1% niobium pentoxide as in other measurements. So, but there is a more important difference. The difference of dispersion between the low temperature reduction and the high temperature reduction. For example, on 0.5% or on 2% platinum content, or even at 10% platinum content. So in each case, when we have niobia, the dispersion of the platinum is lower after the high temperature reduction. So what is the reason? Maybe just the sintering of the platinum. So but maybe not. So let's have a look at the platinum size as determined from X-ray diffraction measurements. Platinum sizes are indicated on after low temperature reduction and after high temperature reduction for a lot of catalyst samples. But what is interesting to see that there is only a slight change between the platinum crystallite sizes, and the change is so the particle size is sometimes bigger or sometimes smaller after high temperature reduction, but the changes are not really big. It means that, as we expected, we see here some strong metal support interaction. That is, after the high temperature reduction, we got smaller CO chemisorption, and for the same particle size, it means that niobia decorated the platinum surface, leaving less space for CO chemisorption, which resulted in a smaller dispersion. There is some method of quantifying this strong metal support interaction. If I can count a crystallite size from X-ray diffraction and from the CO chemisorption as well, I can compare these two sizes. These are different catalyst samples, and in each case I have a low temperature and a high temperature reduction. And I calculated the ratio of the platinum sizes calculated by these two methods. The exact values are not interesting, only the difference between the two treatments. If I have 0 or only 1% niobia, there is not too much difference between the ratio, the size ratio after the two treatments. But in the case of 5% niobia or 20% niobia, there is a much bigger difference. This difference is proportional to the strong metal support interaction. But this separation of the platinum surface is accompanied by some niobia reduction or not. To decide this, we make some hydrogen-oxygen titrations. If the niobia remains unchanged during hydrogen or oxygen titration, then I have to get an OH ratio of 1.5, or in the case of hydrogen spillover, lower than 1.5. But if there is some reduction of the niobia, then I have to get an OH ratio bigger than 1.5. what are the results of this oxygen-hydrogen titration? There are 4 catalyst samples here and 4 pretreatments. First group, pretreatment, the normal treatment, low temperature oxidation, low temperature reduction. It is the low temperature oxidation, high temperature reduction. So this group and this group means the high temperature reduction experiment. The lower 2 catalysts are the catalysts without niobia, with different platinum content. The higher parts indicate the 2 catalyst samples with niobia. So the theoretical limit would be 1.5. We can see that when we add niobia to the catalyst samples, we get an OH ratio always much higher than 1.5. And when we apply high temperature reduction, these values also increase. It is after low temperature oxidation increasement and after high temperature oxidation, low temperature reduction, high temperature reduction. So it means that some reduction of the niobia occurs. So now we know that the catalyst surface is partly covered by the somewhat reduced niobia species. It's sure it is a geometric effect as it is well known from the literature, but we would like to see if there is some electronic effect, some ligand effect in this case or not. So we made some CO chemisorptions studied by infrared on 4 catalyst samples. First, we calculated the ratio of the breached CO and the linear CO peak. The first catalyst sample is without niobia. All the others are with 5% niobia. And we have seen a low temperature and a high temperature reduction. So this ratio of breached and linear CO is quite different in the 2 catalyst groups. The ratio is much higher in the case of the platinum aluminum oxide, and it is much lower with niobia. And even when I apply a high temperature reduction, this ratio becomes much smaller when I have niobia. What does it mean? The addition of niobia, the decoration of the platinum surface, produces much less breached carbon monoxide. But let's see the ligand effect. If I want to see the ligand effect, I have to compare the CO peak positions on this catalyst. So both the linear and the breached CO peak are studied after some low temperature and high temperature reduction. For technical reasons, the high temperature reduction here was somewhat lower than for the other measurements. So the difference is not really so striking. But we can observe that with or without niobia, after low temperature reduction, there is no change or almost no change in the peak position. There is no change in the peak position after high temperature reduction if I have no niobia first row, and also for breached CO. But if I have niobia and I apply a high temperature reduction, then the peak position shifts to a higher number, which indicates that along the metal support or metal promoter interface, some electronic effect also must be operating. Now let's have a look at the reactions. First, the CO hydrogenation reaction. It is it's the turnover frequency of the overall rate of CO hydrogenation. There are different groups in the different pretreatment conditions. What you have to see here. So this peak and this peak are the catalysts without niobia, and this peak and this one are with niobia. So when I apply, when I add niobia to the catalyst, for example at 10% platinum, the rate is increased. or 0.5% platinum, when I add niobia, the rate is increased again. But when I apply a high temperature reduction, then in the case of 10% platinum, I have an increase in the rate, and when I have a 0.5% platinum, there is a decrease in the reaction rate after high temperature reduction treatment. Let's have a look at the selectivities of the oxygenate. These are mostly methanol and demethylators. The same catalyst and the same groups are here. So for 10% platinum, if I add niobia, there is an increase in alcohol selectivity. For 0.5% platinum, when I add niobia, there is again an increase in selectivity. And if I apply a high temperature treatment, then for 10% platinum, high temperature reduction is good for the methanol formation, but for 0.5% platinum, the high temperature reduction when I have niobia is bad for the alcohol formation. So the conclusion is that adding niobium pentoxide to the platinum aluminum oxide catalyst is good for the alcohol formation and for the overall reaction rate, but the high temperature treatment has some more complex effects. So it is obvious that not only when I add the niobia and I apply different treatments, not only the metal support interface length is changed, that is one of the most important parameters, we believe, but this electronic interaction has some other effect on this reaction. So to study the reactivity of methanol, we made this hydrogen deuterium exchange experiment. First, let me show you some results of these reactions. First, the reaction rate of the formation of monodeuteраted methanol. So that means that monodeuteраted methanol has the deuterium mostly on the oxygen. So as it is obvious from simple chemistry. But when I have a look at the reaction rate for the formation of monodeuteраted methanol in the function of the niobia content, I can see some differences. First, there is not too much difference between the low temperature and high temperature measurement, but the chloride content is quite important. With no chloride and with chloride, I have quite different curves. So what is important here? If I add the niobia, then I cover a bigger and bigger part of the aluminum oxide surface. The surface acidity will be somewhat lower. I mean the concentration of the Lewis acid site. That is the property of the niobium pentoxide. But the metal support interface are increased, and this must help the hydrogen spillover to the support. Maybe this is indicated by the increasing exchange in the event of no chloride. The chloride content, I think I will have no time to speak too much about the chloride, but now what I would like to show instead is the reaction rate of the much more important multiple exchange. So the usual figure, we have the different treatment after low temperature reduction and high temperature reduction. We can compare samples without niobia. These are the first part. Without niobia, treatment has no effect or no dramatic effect on the multiple exchange, on the turnover frequency of the multiple exchange. Same is true with another 0.5% platinum sample without niobia. But if I have niobia, either at 10% platinum, either at 0.5% platinum or 2% platinum, I will have some very typical curve. So if I make a high temperature reduction, there is an increase in the multiple exchange rate. It is true for this sample and for 5% platinum, 5% niobium, for 1% niobium, and for 20% niobium as well. The most striking data is for 20% niobium after high temperature oxidation, high temperature reduction. So how can we explain this data? We believe that we have changed the method support interface by adding niobia so that the niobia is partly situated on the aluminum oxide that partly covers the platinum. So different sides are generated. Let's go from the right to the left. So first we can see a methoxy group in the usual manner chemicals on the aluminum oxide. You can see that the Lewis acid centers are sometimes diminished by adding niobia. We have the same bridge type methanol as we have seen on the platinum aluminum oxide, but we have another type of metal support interface, platinum and niobia. The niobia is partly reduced, so these sides, which are which are generated during reduction, can have the methanol to chemical on this bridge type manner, which much increases the rate of the formation of methanol containing more than one deuterium atom. So as my time is over, I think just one more transparency. We can calculate the ratio of the single and multiple exchange. And if we have a look in at this figure in the function of the niobia content, we can see a general trend that increasing the niobia content, we have more and more multiple or less and less single exchange. The exception are these 2 points. These are the catalysts with 20% niobia after high temperature reduction. In this case, as indicated by a lot of measurements, there are so small free platinum surface that the majority of the exchange proceeds on the support on the different oxides, and that must be a single exchange. So I think that's all. Thank you for your attention.
For this guy.
I'd just like to know, when you show a ratio of linear to bridge zero, do you take into consideration different extension coefficients for the two species, or is it just a ratio of absorbances?
Yes, it's just the ratio of the absorbances, so I cannot tell you that the exact values are too much significant. But I believe that when I compare different catalysts, the experimental error or the error arising from this fact that I don't know the extinction current extinction, so this will fall out.
They are indeed different, but nevertheless you can see it very often that there have been ensemble effects and the bridge form is diminishing there. If there are no further questions, we are heavily running out of time, so I think we should continue.